Okay, so anyway, so we're here. These things are very stable. They're going to stay the same. This can get lost to make a lead 2 plus, and then this can get lost with this and make lead 4 plus. So sometimes it's helpful to know why, but sometimes telling you why is just too much information, but maybe this time not. Okay, so that's how we can make those common oxidation states and common transition metal charges. Let's finish. All right, 10. Who's helping me? Tara. Oh, darn it, she just left. All right, I'll be Tara. Okay, so.
Voices get higher.
10.
No, Tara did.
Oh, it's Zoe. I'm sorry. Go for it, Zoe. 10.
Okay, I have 10 plus 2H plus yields 10-2 and 2 or hydrogen gas.
Okay, you could do 10-2 or am I at? Oh, hydrogen. Or what?
Or you
You can do 10-4, and it would just be double. Yeah.
Okay, I was that happens a lot when I'm like doing, when we're doing some of the other worksheets. So how do you know whenever?
Commonly, it will oxidize to the highest oxidation state it has, which means it loses as many electrons as it can. In this case, it would be 4. That would be the more stable one. On your common reducing agents little list, it went from any metal to its highest oxidation state. That's literally what it says. But this is possible. It's just there's other options, and I would still count them both, right? All right.
If you have something like iron 2 chloride, and you're trying to and you have something else, and you know one of them is like 4 or 6, so do you use the chlorine and iron can react? Do you just figure out which one is the opposite?
And then take your 10 and say, okay, is it going to go up to 4 or down to 0? Yeah. All right, next one. Yeah. It would be 10 plus 4H plus yields SN 4 plus 2H2. The only reason is because since this one's going from 10 to 10-2, that's losing 2 electrons. So this one has, losing 2 electrons is going to be gaining 2 electrons. So if 10 goes to 10-4, it's going to be 4 electrons transferred. So that's why this gets a 4, and then double that over there. Okay, Zoe, last one, zinc.
zinc plus 2H plus yields 2.
Okay, so we see that this hydrogen gas formation is occurring a lot with what types of metals? Transition, but they're also there should be more active than the hydrogen on our hydrogen activity series. And there's something called the reduction potential list. You'll get when we get to redox. To electrochemistry. So that's sometimes helpful, but we're gonna mess with that mess later. Okay. So we do see a lot of transition metals, but hydrogen. Not hydrogen. Hydrochloric acid is what kind of acid? I'm dropping down to 1 and 2 down here. It is a strong acid. Is it oxidizing or non-oxidizing? Non-oxidizing, because it's hydrochloric acid itself will commonly go H plus to hydrogen gas, which is going from a 1 plus oxidation state to a 0, which itself is being what? Reduced. So if it's a non-oxidizing acid, the H plus cation is going to be producing something that whatever it can produce after itself is reduced. It's not oxidizing. Whose answer was that? You. Can you elaborate more? Anything else on here? I think that was that's number 3. This one. I'll come back to whatever that number is. All right, go to number 3. Tell me more.
Okay, well, I was thinking HCl because I was thinking really any of the halogens because I mean they want to gain an electron,
Okay.
but I knew you needed an
But they already have an electron, for example, HCl, right?
yeah. Well, then I guess my train of thought was wrong.
Well, go for it. Tell me more about your train of thought.
Because I was really just thinking, okay, the halogens really want an electron, so they would be more willing to be reduced, or to be reduced. So
But it's already the halide form, so itself has been reduced, right? It's normally reduced to its maximum state, right? Because we can't give chlorine any more electrons because it'd be chlorine -2. We've never heard of that in our life. So the only thing that's capable of doing anything is the hydrogen. So memorize this, write it down something. Strongest oxidizing agent. Strongest oxidizing agent means that itself is what? Reduced. It is not. It's forcing somebody else to lose electrons. It's like, give them to me. I want them. Because it needs to be reduced, okay? So strongest oxidizing agent in a non-oxidizing acid is, our 2 options are H with a 1 plus oxidation state or some sort of anion. Commonly, we'll see HCl as a non-oxidizing acid, and cold sulfuric acid is a non-oxidizing acid. Cold. very specific. So the thing that's reduced is the H plus forming hydrogen gas. It has gained electrons. So non-oxidizing acid has the cation reacting or doing the work. It's being reduced.
Does it have anything to do with the fact that it's a strong acid?
No, not necessarily.
Okay.
Because a strong oxidizing agent just means that it's really likely to steal somebody's electrons.
Okay.
Not that it's strong acid means 100% dissociation. Two different things. Let's bounce to who is my strongest oxidizing agent in oxidizing acid.
Me.
Go for it. Tell me more.
Okay, so it's like pretty much the opposite of the non-oxidized agent.
Okay.
Because instead of your cation reacting, you want your anion to react,
And when you say react, you mean what here?
to be reduced.
Right, to be reduced. So commonly, that's reduced. So oxidizing acid anion, AAO, all vowels come together, something there, okay? What's a common example of that one?
HNO3.
Right, so we had that example of copper solid plus HNO3 concentrated. What did that yield?
Copper 2 plus
NO2 gas, right? So here, I'm sorry, nitric acid, what's the oxidation state of everything?
nitrate, or the N is +5, and L is +2.
This one, got you. This one?
And then the ether, it's +3, +4, and then -2.
Okay, so we went from a 5 plus to a 4 plus. What happened? Gained electrons, so it was reduced, right? The anion has something in it that's going to be reduced. Those are the hardest kind of questions because it's memorization and it's not something we encounter a lot. Sorry, but it's there. We just have to be able to be ready for it if we see it. All right, that's not number 6. Number 2, who is the number 2 person? Grace. Go for it.
Okay, so I said that aluminum is more reactive than iron.
Keep going.
And then for the second one, I had wrong first because I looked up an activity series. I looked at whack because it gave me the wrong answer, but I think nickel is more reactive.
Nickel. Remember how it said the general activity series? Go with your gut. Your first one was correct. Yeah. It's the general activity series because there are things in there that kind of waver against the rules. It is before zinc in the first row, but it's zinc. Zinc is commonly like super reactive. All right, and last one. Yeah, that's easy because that's a totally different category of elements, and those are more active based on the fact that they will force hydrochloric acids, hydrogen to do what? So this will be reduced, right? So these are commonly active because they're going to be giving away their electrons. They're readily going to be losing electrons, okay? I keep repeating the same thing because this is like verbiage because we have to read this. Who's the next one? Read number 5. Sonia? Left me. Okay. I got
So
you.
heartless.
Huh?
We're just so heartless.
Actually, I might just have her do that and get that. Grant, go number 6 for me. Use the concept of oxidation reduction to explain why copper is not reactive with hydrochloric acid.
Copper is a lot lower on the activity series than the hydrogen gas would be, so it doesn't react.
Okay, so concept of oxidation reduction. Give me some good, healthy vocabulary terms to put in here.
Copper doesn't have the electrons to give away to react with hydrogen.
Okay, it does have the electrons because we know it can form a 2 plus charge, right? But is it greedy for electrons? Does it want to keep its electrons? Make a choice. It's yes or no. Why does it want to keep its electrons? Because it is not it's not active. It is true to say reactive, but I'm trying to get you guys to say the word active means to be able to do what? Give away electrons or oxidize, right? So copper is not likely to lose electrons because not active. So it's not going to be a very good reducing agent. Yes?
Yes.
So what you're comparing here is the fact that who wants to be reduced?
Hydrogen to hydrogen.
Right, hydrogen and the hydrochloric acid. So we have our hydrogen here that wants to do this. All right, so it's being reduced, right? So it needs some of these electrons. Well, who's the stronger reducing agent? No, Taylor's. Who's the weaker oxidizing agent? Yeah, I was right the first time. Who's the weaker reducing agent? So weaker reducing agent means it's right, weakly going to be giving away electrons. So if copper's not willing to give it up, then it can still happen. Okay, that's essentially what it means. It cannot react with hydrochloric acid. But who's stronger? Who's going to force copper to react? Not in this example.
Something.
Nitric acid, yes. So hydrochloric acid is a good example of what type of acid? Non-oxidizing. So it's just not able to force copper to give up its electrons. But nitric acid is, so it can do that. Okay, so the different abilities of the acids do make a difference. Acidic anhydride, give me, Jordan, give me an example. Well, we did a lot of examples, but give me one good one.
Like the definition of
Definition and an example.
it's acidic oxide, which is like a non-metal oxide, which dissolves in water to form
Okay, so that's one that we commonly use in class. What's another one that you guys can think of that's commonly, well, actually, no, I was going to say this was from, okay, let me give you another example. Phosphorus plus oxygen yields. Phosphorus, I'll do P4, no. Plus oxygen yields. P4O10. Okay. Just go with me here. What does that produce when that non-metal oxide reacts with water? Huh? Okay, sorry, I don't want to put the P first. Just did. Phosphoric acid. What is the oxidation state of this phosphorus? That's -2.
plus 5.
So you got -20 divided by 4 plus 5. And then here, what is it? Plus 5. So this phosphate as a whole is a -3. That's a -2. -2 times 4, -8. -8 plus something equals -3. That would be a plus 5. It's not always going to happen, but commonly your oxidation state of the individual nonmetal will stay really close to the same, if not the same. It doesn't happen all the time, but it's really common to see that. So if you're ever struggling with like, well, I don't know, does it make phosphoric acid, phosphorus acid, hydrophosphoric was something like that acid, phosphoric acid, then you can always try out the transition states and determine which one it is. Next. Daniel.
So I put that basic anhydride is a base without water.
Okay.
So like CaO.
Okay, so a metal oxide is essentially what that is. Okay. All right. So add that to water. What do you get?
Also hydroxide solid.
Okay, which is a base. So basic anhydrides make basic solutions. Do I want anything else on that? Oh, we're good. Okay. Defined combustion is cancel. I'll let him do it when he gets back. Shana, number 10. Tell me, the benzene ones.
Got 2C6H6 plus oxygen gas yields 12 CO2 6 moles.
Okay. So why did you choose when I said excess oxygen? Why did you choose to make that product?
Because it would react completely with the oxygen.
So it's complete combustion, yes? Okay. This next one has propane, but with a limited supply of oxygen. Go for it.
A C3, 2C3H8 plus 7O2 yields 6CO plus 8 forms.
Okay. So why is this one forming carbon monoxide?
Because it isn't able to react completely since the oxygen is limited.
So it wasn't able to oxidize completely? Because here our oxidation state of carbon is what? Here.
4 plus.
4 plus. Here. 2 plus. So it hasn't lost its maximum number of electrons. That's why it wasn't completely able to oxidize. Who's my next person? Allison, go for it.
Okay, 2C21H44 plus 43O2 yields 42CO plus 44H.
Go for it again. 43, O2. Give it to me again.
42.
This one says very limited. So what would be produced? Anybody? Just carbon, okay? So that's what your numbers look like. Okay, so let's go back. Let's just do the products first. We know we're adding oxygen because that's what combustion is. Limited supply of oxygen yields what? Anybody? C, just straight carbon. And water still. That's like when you put a candle out and you put like a little glass lid back on, it makes that black ring on the inside your candle. It's because it's severely limiting the amount of oxygen, so it can't completely combust the rest of the carbon dioxide. This thing, whatever your waxy substance is in the candle, so it makes soot, carbon soot. So that one is going to be 0. And then that balancing is 11, 21, 22. And then last one, plenty of oxygen.
So it's C6H12O6, 6,
So this is also known as
Cellular respiration plus 36 ATP.
36 ATP. Aerobic cellular respiration. Let's get specific here, people.
What?
Aerobic cellular respiration.
Yeah, it's aerobic.
This is biology. You don't have to know how many ATP are there, but this is biology, people.
I don't remember bio. What's bio?
Do you remember the photosynthesis dance? Okay, stand up. We're doing this right now. Stand up. I'm doing this on the video. Ready? You have to do this with me. You gotta stand up anyway. You gotta take a break. All right, ready? The sun and the rain. Come on. Let's start over. Say it with me. The sun
And the rain.
and the sea. O2 makes food and oxygen for me and you. So, what is the photosynthesis equation? Say it with me.
The sun
And the rain.
and the
CO2.
Food, aka what?
ATP.
No. And
Oxygen.
For me and you.
thank you.
That's cute.
Okay,
You never just.
I learned it, but I just never.
so photosynthesis, and then flip it, and you have cellular respiration. We should be aware of this for everyday life. Okay, so on this right here, we have to be able to relate Beer's law. Beer's law is, I'm gonna write on the board. Write this down for me, because I can't write on that right now. Okay, yeah, that's your sheet. That's the most brief version of this lab I can make. Okay, so you can see we're comparing concentration, solutions, wavelength, and absorbance. Remember your absorbance formula that you used when we did the blue food coloring solution? You said negative log of T transmittance yielded A for absorbance, and you had your little graph, and you had the absorbance values, and then negative log T was your y-axis to my memory, and your calibration curve, and you said, okay, well, if I knew the, you had concentration down here, not absorbance, sorry. So you said, okay, well, if I know my concentration, I could go up here and say, okay, well, that's going to yield me, such and such transmittance. But if I give you an unknown concentration, you would find the transmittance, plug it into negative log, and then you would go over to the line and drop down and find an unknown concentration. Remember that from like way back, Okay. So that's called a calibration curve, because what you did was you took all this data and you plugged it into these different types of formulas. We did like negative log of T, 1 over T, 1 over log of T. We did all these things, and we figured out which one's the best linear fit, best R squared value. That is a tool we're going to use for the, probably 5 more units. Okay, so being able to do linear regression and determine what data yields a linear line, that's really helpful. Because straight lines are way easier to work with than curvy lines. Because you can predict things from them, because they should yield some sort of pattern. This is a direct relationship. Increasing concentration, increased the absorbance, which is what is equal to the negative log of T. So we did something like that. But in this lab, you're using absorbance, wavelength, and concentration. So we basically last time looked at only at concentration and absorbance. Now because I told you what wavelength to set your spec 20 at, it was like 470 or something like that nanometers. Now what you see, I'm going to walk through this in a second. You see different wavelengths measuring the absorption of this particular species, this particular solution, copper 2 nitrate. What color is copper 2 nitrate? Copper?
No, it's green.
Blue. Blue. Copper 2 is blue. Copper 2 is blue. Make a little jingle out of it. Copper 2 is blue. Okay, so copper 2 nitrate is a blue color. What happens here is whenever you put different wavelengths on the spec 20s or on something called a colorimeter, the solution is here, the wavelength shines through. If it gets absorbed by the chemicals, what doesn't happen? It doesn't get transmitted, right? It gets absorbed. So that sometimes will make our values very, very weird if we're not using the right wavelength. So if I have a blue solution and I shine blue light through, what happens? Nothing. You guys, okay, so Grant's shirt's blue. Why is it blue?
It's absorbing everything.
It's reflecting, right? It's reflecting like back blue to my eyes. Okay, green shirt's reflecting green back. So if I have a blue solution and shine blue through, it's going to bounce right back, and it gives you misreadings. So what you do is you look on a color wheel, like an art, and you say, okay, what color is the opposite of the color of my solution? So if I have a blue solution, orange is the opposite on the color wheel, something like that. So you use that, and that gives you the best data. That's what we have to know what color solutions are, and it helps us design labs better and get better data, so we can have better correlations and better formulas. So what this shows is we have a maximum absorption at 670, 650 nanometers. Write this down as well. Hold on. I have to remember my cheesy way of remembering the electromagnetic spectrum. Gonna X your voice in my radio. Okay, gamma, X-ray, UV, visible, IR, microwave, radio waves. Which are the shortest waves?
Radio.
Radio, they travel, they're like huge. They're like really, literally meters long.
Gamma.
Okay, gamma. Gamma is what's, made the Hulk. We all know the Hulk. Okay, so watch some cartoons, people. Okay, so gamma rays are the shortest wavelengths. Radio waves actually are like 3 to 5 to 6 meters long. They're huge. They're bigger than we are. Okay, they fly through the air and hit your radio towers. Frequencies get converted to like 92.5 or well, I don't really listen to radio. Pandora is what I play. I can't even remember a specific radio station right now. 95.1. Those are frequencies. Those are megahertz. So a frequency that correlates to a specific wavelength will be what's transmitting to your radio. It's all chemistry, people. Okay, so these are the longest wavelengths. All right, this is not exactly related to that, but I want to go ahead and tell you this. How did I remember this? Gonna X your voice in my radio. I made it up. It's cheesy, but it works. What area do we see here? We see the visible. Why do you think it's called UV? What's UV stand for?
Ultraviolet.
Ultraviolet. So what color is on this side of the electromagnetic spectrum? Violet. Why do you think it's called infrared? Red.
Because red's on the other side.
Red's on the other side. Roy, G.
Oh my god.
It's just backwards. Okay, everything. Hi. So one second. Orange is 670. Blue is about 400. Right this way. Yeah. Oh, poor baby. Yeah, I just gotcha. Thank you. Okay, so that's why, even though it's blue colored solution, we're going with the orange colored wavelength. Okay, so if I gave you red, we would be looking for more on the 400 side, that side. If we had a red solution like red Gatorade or something, we'd be plugging in values closer to the violet region. Okay, so that just helps you determine what wavelengths are. You remember like C is equal to, so speed of light is equal to wavelength times frequency from honors chem. C is equal to wavelength times frequency. Energy is equal to Planck's constant times frequency. We're going to do that in the spring. I'm not going to mess with it right now, but it's there. Okay, so peak here is 670. So we would set our spec 20 at 670 to gather all of our information on copper 2 nitrate. Same thing here, copper 2 sulfate. What's common here? What's our peak observance wavelength? So a little on that side of stuff, and there's about the same, 670, 680. So why is that the same? It's still copper 2. So the same ions need to be working with the same wavelengths because they have a common thing called the molar absorptivity value, which is little a, and I'll put that on the board in a second. Look at this one. Flat line. Why? It's clear. It has nothing. It's going to be, nothing's absorbed, all of it's transmitted because it's clear. Give me another solution that would be clear.
Water.
Give me something AP level. Okay, hydrogen peroxide, give me more. I want an ionic solution. Nitric acid, okay. Sodium chloride, potassium chloride, magnesium chloride, beryllium chloride, lithium chloride, any of those alkali and alkaline earth metals. Goal here is to know that all alkali and alkaline earth metals have no color. Cool? They're not transition metals. Now, transition metals, not all of them have colors, but a lot of them do have colors. So colored compounds, I guarantee you will have a transition metal in them. Okay? Cobalt is pink. Permanganate and manganese are pinks and purples. Copper is green and blue. Iron is yellow and orange and greenish. Zinc does not have a color, sorry. Lead does not have a color, sorry. I don't remember what Wolfram's is, but... And that's tungsten, because it was named after Wolfram. I always say W is Wolfram. It was named after the guy. It's called tungsten. It's not Wolfram. I do that all the time. Okay, iron here, its peak here is about 400. So what color is iron?
Red and blue. You just said
It says orangish yellow. So it's absorbing at the violet blue area because it's opposite on the color wheel. So it's on the orange yellow side. Yes, yes? Look at you guys, little light bulbs going off. Okay. So, question 1, why do we want to use a particular wavelength when determining the absorption of a particular chemical species? The reason we have to do that is because if we use the correct wavelength, we get the correct absorption values. If not, you get wacky absorption values. And is it important to measure absorption for all wavelengths from 400 to 700? That's only if you don't know the particular wavelength you should be working with. So yes, if it's an unknown, but if I tell you you're going with 670 or 420 or something like that, that's because I've already done that pre-lab work for you. Okay, here's Beer's Law. This is what I wrote down. If one were an adult and we're over 21, where would one go to get hardcore alcohol?
ABC store.
ABC store. Okay, that is not where you would go. Another story. All right, you go to the ABC store. A is equal to A, B, C. This is called Beer's Law. This is not where people go to get beer, but that is called Beer's Law. And I remember it's because it's the ABC store. Okay, A here is absorbance. A little a here is molar absorptivity. B is path length, aka width of cuvette. Why do we have to use the same cuvette in all trials then?
So it's the same.
So it's controlled, right? So it's the same. C is concentration of that particular substance. All right, so what is directly related here? What variables are directly related? Concentration here.
molar absorptivity.
What if I tell you this is a constant? You can't change it. Constant.
No, A and C.
A and C, thank you. Big A, absorption, is directly related to concentration. If I increase the concentration of something, what's going to happen to the transmittance? through the solution?
Less.
It's going to become less. So the opposite of transmittance is absorption. So increased concentration will increase absorbance. B stays the same and A stays the same because B is referring to your cuvette, which you should keep the same for the entire duration of all trials, meaning it's a controlled variable. The A is specific to your substance that you're using. So A values are not going to be like commonly published all the time. A lot of times we have to figure out the A value is based on us knowing concentration, us knowing absorbance. So that's going to be different between copper 2 and iron 3 and copper 1 and zinc. I mean, it's going to be different for everything. So that a little A value is a lot of times what we find out because they don't always publish them. Okay, so when you're looking through here, A is the molar absorptivity constant, whose value depends on wavelength. So why would we need to do an experiment with the same wavelength for all trials? Okay, to make sure you're getting the right absorbance. But if I change the wavelength that I'm measuring these things at, these absorption values at, what is also going to change? The molar absorptivity, and I can't have that change because then I have 2 and 3 variables changing in an experiment, and that's not controlled. You can't have confidence in your values. You can't have confidence in anything if more things than one variable is being changed. Yeah.
Isn't there another way to write it? Like it looks like a backwards 3 and L and W.
That's I forget what Greek letter that is. I guess a Greek letter A, but this is a lot of times the way we'll see it is ABC. I gotta look at your reference tables though, so I can see how it's written on here. So that's why we always use the same wavelength so that our molar absorptivity value doesn't change. So we can directly correlate these two, big A and little c. All right, I think that's all I really want to talk about. Optimal wavelength for copper 2 nitrate, we saw it. Here's the actual graph. Optimal wavelength for collection would be at the peak. Anytime you have an inflection in a graph, it's usually the thing you're supposed to be looking at. It's like a titration, you're looking at the equivalence point. Absorption graphs, you look at the
Attention teachers, those students that were in the PSAT meeting are headed back to their classroom. Samantha Coon, I need for you to come to the front office. Thank you.
Okay, so this right here is a little bit more reading on Beer's law. I'll let you guys do that. This right here is the graph we just talked about. We commonly will do concentration versus absorbance, but absorbance also can be written as negative log of T. And this is where we'd use this. I will tell you really briefly on this, the uses, the FYI facts. How does the absorbed light, or sorry, what is the version of energy due to the molecule? UV, high energy, it ionizes, it makes ions. Okay, you have to know if you shine UV light on something, it commonly will cause electrons to bounce out and make it an ion. Low energy, so like red light, it will promote electrons. So there's this thing called the photoelectric effect, which is related to that. Hi. Hi, how are you right now? Just jump in. There's something called the photoelectric effect. Photoelectric effect. Photo refers to what? Light. Electron. Electric refers to what? Electrons. Alright, so what happens is light excites electrons and it causes them to bounce around. When they bounce around, they can be promoted to higher energy levels. That's what that right there refers to. IR, do this for me. Okay, you're carbon dioxide. Where's carbon? Someplace on you. Where's carbon? Carbon dioxide. Think your head, right? Carbon dioxide, CO2, C goes in the middle. What are your hands? Oxygen. Oxygen. What is bonded? What are your arms? The double bonds. Okay, so it's a double bond feature. What IR does is it goes like this. Okay, it makes them vibrate. The little bonds just go like this the whole time. So you can do like the Egyptian, you can do this whole, it just makes them just do this, okay? We're dancing now. But that's all, it just makes them vibrate, and that's all I'm going to do for now. Alright, the rest of these are later. We've got labs with Spec 20s and spectroscopy for the rest of your life, so that's why I had to go through this in excruciating detail. Okay, the rest of the time, I'll have those people tell me their answers to the couple of questions we missed earlier. In a little bit, work on your Redox in real life if you want. I have the computers, which I hope nobody needs because nobody came with them. I have those computers in the back. You can work on labs. You can work on unit reviews. Be productive. Don't get off task.
Can we sing our song?
Oh, you can show them the song. Yeah.
When's the Redox
In real life,
project? Yeah.
Monday. I'm gonna do Monday. That's not that important. All right, get to work. Let's go. Do we all need to do it real fast? Okay, stand up. Because I offered extra credit, so they need to see it. Okay. Wait. All right. Ready? And 1, 2, 3, go. The sun and the wind and the sea. O2. Mixed food and oxygen. For me and you. Okay, thank you. If you did that for a teacher and they email me, extra credit.
Yeah.
Yeah,
like right now.
Alright.
If I get multiple teachers email me, going to Mark.
I thought she had a corporate plan.
I shall do it. Okay, gotta go. I'll do it. The sun. You know, I don't want to do it.
Oh, I gotta. Everything.